All right, taking a look here for problem number 1, we want to compare the experimental and theoretical probabilities of landing on heads for tossing a coin. So who can raise their hand and tell me what is the theoretical probability that we're going to land on heads when we toss a coin? Theoretical, Tyler? 50%, right? Because when we're talking about landing on heads theoretically is just focusing on the fact that we've got a coin. I tell you we have a coin, that's what we focus on for theoretical probability. Okay, so theoretically, the probability that we're going to land on heads is 1 out of 2, right? One side of the coin has heads on it, the other side has tails, so it's 1 out of 2, which comes out to 0.5, which comes out to 50%. Okay, experimentally, what is the probability that we are landing on heads? Io. Not 15 over 25. No, 14 over 25. Yeah, 14 over 25. So experimentally, that's when we focus on the fact that we tossed the coin 50 times and it landed on heads 28 of those times. So that's the actual data. That's the experiment. Okay, so experimentally, when we tossed the coin, it landed on heads 28 times out of the 50, which simplifies to 14 over 25. If you convert that into a decimal, it would be 0.56, which is 56%. Okay, so then when we're comparing them, then we know, hey, experimental data or experimental probability of 56% is greater than the theoretical probability of 50%. Okay, which we can understand, again, that they're not going to be identical. They're not going to be the same, because what do we need to make sure we do when they're not the same? More trials, right? Even says it right down here at the very, very bottom as our big reminder. If they are not the same, if your experimental probability is not the same as your theoretical, then you got to perform it more trials. Okay, you got to keep going with the experiment. Okay, that was the number one thing that you guys were messing up on last week when you were doing your quiz and you were having to type out, okay, which one of those experimental probabilities is a better representation. You had to either choose the independent one, which was just you, versus the class one. The class one was a better representation, right? Because as a class, when we put it all together, it represented more trials. The more trials, the better the results, okay? So you want to always keep that in mind. The more times that you're performing the experiment, the better the results are going to be. All right, number 2. You have 5 green marbles, 2 purple marbles, and 3 blue marbles. So that's the information that they're giving to me. That's the theoretical information. Okay? That's like saying, hey, you have a coin. Here they're saying, hey, you have this many marbles. That's your theoretical. So based off of that information, the theoretical probability that we're going to pull a purple marble is how many purple are there in the bag? How many purple are there? 2. There's 5 green. There's 2 purple. There's 3 blue. So we have 2 purple marbles. Out of how many total marbles are in the bag? 10, right? 5 plus 2 plus 3. 5 plus 2 plus 3 is 10. So 2 out of 10, which would be 1/5. That comes out to 0.2, which is going to be 20%. Okay? Now, the experimental probability. For the experimental probability of pulling purple, that's when we look at the table. This is our experiment. We landed on purple how many times?
5 times.
5 times out of how many total?
45.
45, right? The total here, when we add them all together, was 45. So 5 over 45 simplifies to 1 over 9. That's about 0.11, which is about 11%. Okay, we're estimating. So in this case, hey, our theoretical probability of 20% is now greater than our experimental probability of 11%. And again, that's okay, it's fine. In order for them to become closer, we just have to perform more trials. So we need to pull the marbles out more and document how many times that we're landing on certain colors. Okay? So again, this is a huge thing right here. This reminder. Star it, underline it, circle it, highlight it, do whatever you need to do to remember it. That if you need your probabilities to be mirrors of each other, You got to perform it a large number of tries, trials, times. Not outcomes. The outcomes don't matter. Doesn't matter how many outcomes you have. It's the number of trials that you perform. That's the important thing. All right, go ahead and flip it on over to the back. We're going to be talking about today 2 concepts for our discussions for today. So we actually have 2 parts to our learning target today. Part 1 is that we're going to use probabilities to make predictions about specific outcomes or events. And then part 2, we're going to identify the total number of possible outcomes using what we call FCP, Fundamental Counting Principle. Okay? So with part 1, making predictions, we're going to actually go back to what we did in our ratios and proportions unit, and we're going to be using proportions with probability to be able to create these predictions. So it's important to be able to make predictions in a lot of different situations. So like if I'm a business owner, so for example, number 1, we've got a business here and they're selling a product. Notice that this product is a food item. That food item is perishable, isn't it? Perishable, meaning that if you don't use it, it goes bad, right? Okay, so when I am trying to be a successful business owner, I need to have an idea of how much of my product people are purchasing so that I can have that product in stock for the amount that I feel it needs to be sold at. If I were to over-purchase an item, meaning I purchase way too much of that item, and it's a perishable item, what's the negative thing about that? Isaiah? Yeah, if you don't use it all, if you don't sell it all, it's going to go bad. So then I lose money as a business owner, right? Because I purchased an item, I over-purchased an item, and I didn't sell it, so now I have to throw it away. So I lost money that way. Now, there's an opposite to that. Okay, I'm not going to over-purchase, but what if I under-purchase? What's the negative of under-purchasing? You won't make as much money. Customers might not be happy, right? I go to the store and I'm always saying, oh my God, I want a lemon muffin, and you're always out of lemon muffins. You never have them. Do you think I'm going to keep going to the store? No, I'm probably not going to go there anymore. I'm probably going to go find someplace else that's going to always have my lemon muffin that I want. Okay? So there's a negative to both sides. Under-purchasing and over-purchasing is a thing that happens often in businesses. And wanting to make sure that you have just the right amount. Yes, you might over-purchase, but if you over-purchase on maybe like, oh, I only have to throw away 5 muffins versus I have to throw away 100 muffins. There's a huge difference between that. Or, oh, there's 3 people who came in today that weren't able to get the product that they wanted versus there's 30 people who weren't able to get the product they wanted. There's a difference in that. You're not going to be able to get it to the exact amount. Okay, you are going to sometimes under and over purchase, but you don't want it to be so drastic that it's going to hurt your profits drastically. Okay, so they use probabilities, specifically experimental probabilities. They identify how often do people ask for a product so that they can be prepared to have that predicted amount in store. Okay? All right, so for here, in our example that we've got, yesterday we've got 50 customers that bought muffins. So I'm a muffin store. 50 of my customers came in to buy muffins, and 12 of those muffins were blueberries. So now I need to prepare for Friday. And I know usually on Fridays I get about 75 customers. So I want to prepare for how many blueberry muffins I think I might need to have in stock. Okay, so what I'm taking is I'm taking the information that I know, which is going to be used for my probability. This information that's been provided is my experimental probability. Thank you. Go ahead and grab the packet right there. It's my experimental probability because it is actually what has happened. I am calculating this information, I'm recording this data, and I am noticing that out of my 50 customers, okay, out of the 50 people that came into my store, I had 12 of them that purchased a blueberry muffin, so I'm just going to put blue. I had 12 blueberry muffins from the 50 people that came into my store. So now I am preparing for Friday. So that's where my prediction comes in, because do I know how many exact people are coming in on Friday? No. I'm expecting around this many people, but it's not an exact. So that's going to be my prediction portion. So we're creating what we call the probability prediction proportion. You create your probability, you set it equal to what you're predicting, and you solve it using proportions. So I need to know how many blueberry muffins to make. I don't know how many yet. I'm just going to put that as my variable. If I have 75 people coming in. So I've got 12 over 50 is equal to x over 75. Once I've got it in that format, I can then use my typical cross products to solve. I can multiply my 50 and my x together, and I can multiply my 12 and my 75 together. Okay, so 50 times x gives me 50x. 12 times 75 is going to give me 900. And then from there I can solve. What do I do? Tyler? 900 divided by 50, right? We're going to divide both sides of that equation by 50. And we're expected to make probably about 18 blueberry muffins. Yeah, 18, not 19. Okay. 18 blueberry muffins is a good estimate for what we should make. Now again, I'm not guaranteed to have exactly 75 people come in. I might only have 70. Maybe I have 80. And maybe Friday's not the day that people want blueberry muffins. But this is just giving me an idea based off of previous data that I've recorded. It'll help me make a prediction of future estimations. Okay, let's take a look at problem number 2. Again, same concept. I got a bag of fun-sized Skittles. In that bag of fun-sized Skittles, I have 2 purple, 3 orange, 6 yellow, 1 red, 1 green. God bless you. So if I'm purchasing a king-size bag of Skittles, and the king-size bag of Skittles has 150 Skittles, then I want to know about how many purple should be in the bag. Okay? So again, information that has been provided, data that I have actually collected, that's the information that I can make my probability out of. What color are we focusing on again? Purple. We're focusing on purple. So I have 2 purple. So when I make my probability, I've got 2 purple out of how many total Skittles were inside of that bag? 13. I have 2 purple out of 13 total Skittles inside of that bag. Now I want to make a prediction. I want to predict, hey, I got a king-size bag of 150 Skittles, then how many purple are there? Okay, so when I set up my next ratio, where's 150 going to go? At the bottom, because it's a total, isn't it? I have 150 total Skittles in there. I want to know how many of them are going to be purple, so X is going to go on top. Okay, then we can go ahead and do our cross product. We can do 13 times the X, right? I always like to multiply my variable first. 13 and X, 13X. Then I'm going to multiply the other diagonal, 2 times 150. 2 times 150 is 300. Okay, and then we'll divide. Now, 13 is not going to go into 300 perfectly, so we're just going to estimate it. Okay, round it. What would we round it to? 23. So about 23 purple is what we'll expect to see. Okay, I want you guys to do problems 3 through 5 on your own. You can do them with your table, actually. Do 3 through 5s with your table mates. All right, let's take a look here for problem number 3. What you should have set it up for, you have the probability of pulling a red marble is 2 out of 9. What this means is that for every 9 total marbles that you have, you are pulling out 2 red. That's what the probability is representing, that for every 9 total marbles that you happen to have, you're pulling out 2 red. So what they want to know is if there are 7 reds, then how many total marbles are there going to be? So the 7 this time is going to go on the top because that's representing the reds, and what's missing is the total. That's what's going to go onto the bottom. So you have x total. Then you do your cross product. So we're going to multiply a variable portion first. So 2 times x is 2x. Then we're going to multiply our number portion, 9 times the 7. 9 times 7 is going to give you 63. And then you can go ahead and divide the equation out. Now you are going to get a decimal, but again, you want to go ahead and estimate it. So we're going to say that x is going to come out to approximately 32 total. Okay. For problem number 4, they're giving you a table of information to represent the number of necklaces that were sold in July. So what this means is that in July, he sold 12 12-inch silver necklaces. He sold 22 12-inch gold necklaces. He sold 16 16-inch silver necklaces, 8 16-inch gold necklaces, 5 20-inch silver necklaces. Definitely not appropriate here at school. 12 20-inch gold necklaces. So he has a total of how many necklaces did he sell? 75. If you combine all of this together, that's a total of 75 necklaces that he sold in July. Again, this is the data that he's collecting. If you add all of the silver necklaces together of the varying sizes, and you add all the gold necklaces of the varying sizes together, you get 75 total necklaces that he sold. Okay, so we are focusing on the 20-inch gold necklaces. So how many 20-inch gold necklaces did he sell in July? 12, right? 12 20-inch gold necklaces were sold in July. So we're giving July's probability, right? The probability or experimental probability of July was 12 out of the total 75 that he sold. Now we want to know, hey, if in August he's going to sell 100 necklaces, he thinks he might sell about 100 necklaces, he wants to know how many of those gold 20-inch necklaces should he expect to sell. So x over 100. And then we can do our cross product. We're going to do 75 times the x, which gives us 75x. Then we're going to do our 12 times the 100, which was 1200. And then we can finish it off by dividing. So about how many? 16, right? So 16 necklaces that are 20-inch gold necklaces. 16 of the 20-inch gold necklaces. Okay? All right, last one. If you roll a die 21 times, we want to predict how many of those times would you possibly land on a number greater than or equal to 3. So again, remember, when we set this up, we set it up as the probability of the event, and we're going to set it equal to the prediction we're trying to create. Okay, so what's the probability that we're looking for in this situation? Read the statement again. If you roll a die 21 times, predict around how many times you might land on a number that is greater than or equal to 3. So what probability am I looking for? Probability of a number greater than or equal to 3, right? You're looking for the probability that the number is greater than or equal to 3. So what am I focusing on again? I'm focusing on rolling a die. So you need to find the probability first of rolling a die and landing on a number that's greater than or equal to 3. What's that probability? How many of those numbers can we land on that are greater than or equal to 3? 4, right? There's 4 numbers on here. Shh. That would be the number 3, the number 4, the number 5, and the number 6. That's 4 numbers. There are 4 numbers on a die that are greater than or equal to 3. Out of how many? Out of 6. You got to set up your probability first. So the probability, they're not giving you the probability, they're not giving you data here, so we're actually using our theoretical probability this time. Theoretically, we should roll a 3, a 4, a 5, or a 6 4 out of 6 times. Okay, now we want to make a prediction. The only number up here that's going to be part of my prediction is what number? The 21. Where's that 21 going to go? Top or bottom? On the bottom, right? Because we're going to roll the number die, or roll a cube, or roll the whatever you're going to call it, 21 times. We want to know how often should we expect to land on a 3, 4, 5, or 6 out of those 21 rolls. Okay, so that's how we set that one up. Probability prediction. So then we can do our cross product. I don't worry about you guys doing the cross product. Once you've got it set up, you know how to do the cross product. 6 times x is 6x. 4 times 21 is 84. Okay? The thing you need to make sure that you are working on is setting it up. Find your probability, let it be equal to what you're predicting. Okay? That's what you need to make sure you work on. Okay, and that should be about 14 times. Again, is it exactly going to happen 14 times? No. It's a prediction. Predictions are always estimations. All right, go ahead and flip it to the last page. The last page we're talking about is the FCP, the Fundamental Counting Principle. And what the Fundamental Counting Principle says, Isaac McKenzie. What the Fundamental Counting Principle is saying is that if you've got P ways of doing one thing and Q ways of doing another thing, then when you're doing both of those things simultaneously, you have P times Q ways of doing both. Okay, we did an activity like that last week when we were talking about theoretical versus experimental probability, and we said we had 2 dice. Okay, and we created this whole large sample space using those 2 dice. Okay, we had the probability of landing on any given number on my red die and any given number on my green die, and we created our total sample space. How many total outcomes do you guys remember that we made? More than 6.
12.
See, now 12 is a common mistake. A lot of people look at it and they go, oh, well, I've got 2 of these, and each of them have 6 outcomes, so 2 times 6 is 12. But remember, if you remember, I said, hey, I can land on red staying a 1, and green could be a 1, but red could stay a 1 and green could be a 2. Red could stay a 1 and green could be a 3. Red could stay 1 and green could be 4. Red could be 1 and green would be 5. Red could be 1 and green would be 6. So all these ways, we had 6 ways that red could stay a 1 and green would change. But then, just like Mackenzie figured out, she said 36. How many ways can red change? How many different numbers can red have? 6. Okay, so I had 6 ways that red could stay 1, but I also have 6 ways red can stay 2. I have 6 different ways red can stay 3, and so on and so forth, for all 6 ways that red can change. So you're taking the total number of outcomes of each separate activity and multiplying them together. Let's write that down. So you're taking the total possible outcomes. You should be writing. Total possible outcomes of activity, we'll call it activity A. And then you're going to multiply that by your total possible outcomes of activity B. And then if you have more than that, if you have another activity, then you'd multiply by all the possible outcomes of that activity. And you just keep multiplying by all the possible activities or possible outcomes for each of the activities that you have. Okay, so for example, with problem 1, we've got 8 shirts, 6 jeans, and 3 pairs of shoes. So looking at that, it doesn't look like we have a whole lot of different kind of clothes, but we actually have 144 different outfit combinations that we can create from just that limited amount of items, okay? Because you can pair them all differently. So looking at my shirts is my activity A, which is 8 of them. And then my jeans, or bottoms, whatever you want to call it, that's my activity B. And then I even have an activity C in this case. I've got 3 pairs of shoes. And all I'm going to do is multiply them. So 8 times 6 times 3 comes up with a total of 104 total outfits that we can create. Now, given all of these different kinds of outfits we can create, we can actually find the probability of a specific outfit combination being created. So let's say, given those 8 shirts, 2 of them are white, 3 of them are black, and 3 of them are red. Right? 2 plus 3 plus 3, that gives me my 8 shirts. Out of my 6 pairs of jeans, I have 4 of them that are blue and 2 of them that are black. And out of my 3 pairs of shoes, I have 1 pair that's flip-flops, 1 pair that's sneakers, and 1 pair that's dress shoes. So I want the probability that I'm going to choose an outfit that's a white shirt with black jeans and with dress shoes. So now I'm looking at this specific combination. White shirt. So out of my 8 shirts, I've got 2 of them that are white. So this is the information I'm looking at up here. So the probability of a white shirt is 2 white out of 8 shirts. Then I'm looking at the jeans. So out of my 6 pairs of jeans, 4 of them are blue and 2 of them are black. So I want the probability that I'm just going to choose some black jeans. 2 of them were black out of the 6 total pairs that I have. So the probability for black jeans was 2 out of 6. Then doing the same thing for my shoes. I've got 3 pairs of shoes. Only 1 of them was considered to be a dress shoe. So the probability that I'm going to pick a dress shoe, IO, write this down. I have 1 pair of dress shoes out of the 3 total pairs of shoes that I have. So then all I have to do, just like I did up here with my fundamental counting principle, I multiply those probabilities together. So 2 over 8 times 2 over 6 times 1 over 3, that comes out to a probability of 1 out of 36. So yeah, I have 144 different outfit combinations, but the probability of picking this specific combo is 1 out of 36. All right, I want you guys to do numbers 3 through 5 on your own, please. All right, like I said before, we already talked about problem number 3, the total possible outcomes of 2 dice. We just have 6 possible outcomes for one of the die, and then 6 possible outcomes for the second die. So 6 times 6 is at 36. Okay, total possible outcomes from flipping a dime, a penny, and a quarter. So how many outcomes do we have to flip a dime? 2. There's 2 different outcomes for flipping a dime. How many different outcomes are there to flip a penny? 2. Just the 2 outcomes for flipping a penny. And then how many outcomes are there for flipping a quarter? 2. Okay, so 2 times 2 times 2 means that we have 8 different outcomes that we can land on. Shh. All right, and then problem number 5. We have a 5-section spinner, and then we have a coin. So how many outcomes are there on the spinner? 5. How many outcomes on the coin? 2. So then we're going to do 5 times 2, and that comes out to 10 total outcomes that we can have for them to be combined. All right, your assignment is loaded in Google Classroom. Go ahead and get logged in.